Let's dive in. Okay, so yes, as we gave a little bit of context before, but I'll just reiterate. This is a talk that I originally planned for ETH Denver, but it is a kind of extended version because, of course, I made 300 slides and could not finish reviewing that in 20 minutes. But today we are going to talk about the superchain. It is a superchain explainer. We're trying to go over all of the key concepts so that you can honestly, hopefully build the superchain yourself. So more context. The previous talk that I gave about the superchain and the OP stack was in DevCon, where it was a more kind of non-technical, high-level overview of the OP stack, as well as how that forms the superchain. And it had lots of gerbils and was very, very artsy. This is a little bit more in the weeds. And, you know, we can't have any fun memes in this. So Leroy Jenkins, let's do this. Okay, so the superchain to the rescue. 3 sections. Let's get started. Okay, so blockchain today is insufficient for the decentralized web. Why is that? Well, meet congestion. To be honest, we have so many applications that if this thing would scale, we could achieve. But yet our arch nemesis congestion is always there to ruin our plans. With these insanely high gas prices, you know, $13 for a random transaction, you know, imagine trying to put, you know, Twitter on chain and you had to spend $13 to write games, comma. You know, that doesn't make sense. That does not make sense at all. And realistically, this is not new information that I'm giving here. I've said this a million times. Literally, after Bitcoin's white paper, the first response, or maybe second response, was we very, very much need a system, but the way I understand your proposal, it does not seem to scale to the required size. That is a serious problem, and we have been dealing with it from 2008 all the way till 2023, and we still have not solved it, which is a little bit worrisome, but we are getting so close. We really are, you know, we are getting there. So now, before we get into the technical details, let's just imagine a future where smart contracts were horizontally scalable. I could deploy smart contracts and it would always be nearly free to transact on them and send transactions and do fun little experiments. Imagine if things were different, right? It was not just Doge images. We were actually delivering real value to real users. Well, what would the world look like if it was being run, quote unquote, on the blockchain? Okay, well, one, I actually think that there are some underexplored and under talked about implications of an incredibly horizontally scalable EVM or some similar, you know, smart contracting infrastructure. Because writing smart contracts, it abstracts away all the back-end software stack. I literally, like, you know, back in the day when Hayden was writing Uniswap, I was so mad because Hayden was able to write this, you know, write these smart contracts, deploy them to Ethereum, and then never have to worry about being on call and being, you know, the application going down and all of that stuff. And me, as I'm building out this backend infrastructure, I'm having to get woken up in the middle of the night to fix the server going down, right? If you're writing a protocol and you're deploying it to a network of computers that know how to speak and use that protocol, then people can rely on those computers. And as the protocol author writing the, you know, the application logic, I don't need to worry about the backend infrastructure going down. That's someone else's problem. That is an incredibly valuable thing. And I do think that the EVM is kind of underrated, even in the serverless space in Web 2. You know, a Web 2 EVM would be pretty cool. Anyway, 2, right? With smart contracts communicating with each other, if the more things that are on chain, the more composability we can have. If all of these applications were written as protocols, were written as smart contracts, like things like REST, where you have to, make sure that all of these servers are online and not going down, like that kind of stuff you would not have to worry about it from the application's perspective. Now, let me see what else, right? Okay, developers liberated from infrastructure costs. Well, devs won't need, when I write my application today, if I want to spin up a new, if I want to spin up a backend and I want to horizontally scale my backend because I am, seeing a lot of traffic, I'm getting a lot of usage, what that means is that I now need to bear that infrastructure cost myself and basically start figuring out a way to charge for those services. So for instance, what I'll end up doing is I'll throw ads on my website to make sure that whatever backend compute I'm doing, at least I'm breaking even for this, app that I'm really into, right? That does not necessarily need to be the case. If I'm an application developer, I write the protocol, and then other people, whether it's users directly or even third parties, they can pay for that application server cost. So this is I think this is a genuine, we talk about uses of crypto, and obviously this is not the only uses of crypto, right? There's tons of great decentralization stuff, but I do think that there is a underexplored set of benefits to using these scalable software that is just making the web stack better. So anyway, I'm very excited for that. And I'm excited for that, turning an application backend infrastructure space from a kind of desert into a vibrant ecosystem, because that's what happens when you lower the barrier of entry to building out applications. When people don't have the ability to write horizontally scalable backends, but they can definitely write a smart contract. That is going to be magical. Now, unfortunately, this image is reversed. It actually went the other way in reality because we're killing the environment with sunscreen. So that's the sponsor of our video. No, just kidding. Okay, so imagine writing the Twitter protocol as a, that could scale horizontally to the world as a hackathon project. That might sound insane, but we can talk about it more. Ask me some questions, because I will definitely tell you that it is actually genuinely a thing that can be done. Now, that is, and the whole world powered on the EVM. I know some people are cringing when they see that, but whatever. The whole world powered by a smart contracting, system. And realistically, EVM is looking pretty likely. Anyway, great. The decentralized web can still be realized. That future is still possible, right? We've been working on it for years. Started out working on it with ETH2, then Plasma Group, where we did a bunch of the foundational research, then Optimism, where, what we're doing now, and also a huge industry. This is the beauty of the open source community of Ethereum, of all of these builders. We have been working on building this technology together for so long. It's insane. So that has caused us to finally come up with a good set of abstraction layers, right? This is my favorite quote from a video that with Jim Keller. He's like a chip processor designer. He's really great. If you and what he says is, when things are beautifully done, there's usually a well thought out set of abstraction layers. The fact that we have these abstraction layers is new. It is recent. We are now at the point where we have the abstraction layers, like the equivalent of the network stack for the blockchain stack. And we can then use that to massively scale up development. So this started out with, the whole roll-up centric Ethereum roadmap and ETH2 and L2 and Barry Whitehat, and all of these things have helped us see it clearer that what we need is congestion versus the super chain. There we go. The super chain. Let's go. Okay, so now let's, before we dive into the super chain, all of these abstraction layers that comprise the super chain, let's talk about the basics. Well, first off, the super chain is more than one chain. I know it's called super, but that's the super chain makes it multiple chains that you can abstract into one chain. So why is it more than one chain? Well, scaling to support the internet, it's going to require more than one chain. Why is that? Well, it's because if I'm running a chain, I need to sync a node. And the more transactions, and that's fine for a chain this size, and the more transactions that we shove into that chain, the bigger it gets until I can no longer sync it on my computer. And that is just fundamentally antithetical to, if we had chains that were this big, that would be fundamentally antithetical to the whole point of decentralization. We would no longer be able to verify the compute. It just does not work. So it's not one chain. We need to scale. And if we can't scale, like I can't run all of the internet on my computer. But it's also not multi-chain, because the multi-chain designs that we have today, they're really insufficient, right? Each additional chain in a lot of these systems, the way that they're architected, they add security risk. If I bridge from chain A to chain B to chain C, then it ends up with the weakest link security. If chain B fails, then chain C and chain A are affected. And so that totally doesn't work, because as we add more chains, which we're definitely going to need for getting internet scale, we are compounding that security risk. Additionally, deploying chains oftentimes is considered expensive, right? Like you end up having to think a lot about your verifiers and all this kind of stuff. It doesn't make any sense. Like we need, for us to get to the point where we have internet level scale, we need chains to be fully commoditized. They need to be so easy to spin up, so easy to shut down. Like all of the, you should be able to spin up a chain in your web browser, that level of ease, right? And so that's kind of stretching the definition of what we even think of when we say chains. But so it's not mono chain. It's also not multi-chain. It's super chain. Okay. These are some properties that, I'll go over. We're going to form the intuitions for why these properties make sense and where they come from. But I'll just start out like there's a shared L1 blockchain. So these are all like layer 2s in some, definition of that term. There's also a shared bridge for all of these OP chains, which ensures that the messages between them are authenticated correctly. And we'll talk about that later. Also, cheap OP chain deployment, right? Needs to basically be free. We need configuration options for these OP chains and secure cross-chain messages. So at a high level, you can kind of see it as something along these lines where it's, Ethereum, Optimism bridge, and a bunch of OP chains with a shared messaging protocol. And notably, as these OP chains standardize, then cross-chain dApps get supercharged, because if I'm writing a cross-chain dApp, then I know that all of these chains are going to conform to these exact same properties. Then I can write my application one time and know that it is compatible with any and every chain on the super chain. That allows me, that ability allows me to abstract away the underlying chain that I'm deploying to, and instead start deploying on the super chain directly. Like the future of this kind of deployment is not that you are picking a chain and you're deploying there. It is instead you are writing your application to work on the super chain, period. And that is how we can horizontally scale. So notably, obviously, this is not in production. Like this is coming soon. This is more about giving y'all the intuitions for how to build this thing so that you can help us build the OP stack, build this, the super chain, and, create an open source internet. So yes, it's already been almost a decade. So like definitely tamper your expectations. It's not like a trivial thing to do, but we're closer than ever and you can help too. Great. Very happy. Okay. That is the context. That's the light stuff. That's the easy stuff. Now let's get into the abstraction layers. This is where the meat really is going to be in this talk. Okay. So when things are beautifully done, there's usually a well thought out set of abstraction layers, right? What are those abstraction layers? Well, the first layer, first concept, I'll just call it, is superchain derivation. So what is that? It is the process by which an L2 chain's state is derived. Now, notably, we use derivation in a few different contexts that may, if you look up the op node and you see derivation there, and there might be usages of derivation that are more limited than the way that I'm calling derivation in this talk. I'm kind of talking about derivation as the entire pure function that turns L1 chains into L2 chains. But anyway, sorry, that was just a warning. But this is what derivation, regardless of the word derive, the concept is the same. The concept is that L2 chains are a pure function over the L1 chain. What that means is I'm taking the L1 chain, I'm doing some compute over it, and it's outputting the L2 chain and all of its glory, right? All of the balances, all of the transactions, everything. That is this, full state transition derivation. So what does that look like visually? Because it's much easier to see. Well, first off, you have Ethereum, L1, you call this derive function, and boom, now you've got the red chain, derivation. You've got the blocks in the red chain. And now Alice might take a transaction, send a deposit, for instance, onto Ethereum, and then we do this same derivation process, the same derive function, and that outputs on L2 the L2 chain, which includes the deposit transaction. Fantastic. Now, we might continue. There are no transactions on L2. And so, we keep going. The blocks are empty, but we're still deriving. So blocks are still being produced. It's just this pure function is still working as normal, but nothing's happening. It's not very interesting. And then now Alice might even take a transaction, and instead of sending it directly to L1, she sends it to a sequencer. Then the sequencer takes that transaction and submits it to L1 on her behalf, relays that transaction, and we call derive, and we get the L2 chain from that. Pretty simple. Well, okay, to kind of show what this means, let's talk about a myth that we oftentimes hear when I've described this to a lot of, over and over again. Basically, there's this very clear intuition, which is that sequencers can forge transactions. That is the thing that it feels very intuitive, that a sequencer can submit a transaction, and that is, this big risk vector and centralization vector because they can, steal some money. Okay, let's talk about that. Let's go through that within this mental model. So Alice takes a transaction. She signs that transaction with her private key that only she knows, submits it to the sequencer. The sequencer then changes the recipient, let's say, of the money to the sequencer's address. Now that signature is incorrect, right? The transaction is no longer a valid transaction. Then the sequencer submits that transaction to layer 1. The derive function is then called to get the L2 chain, right? My L2 node is the one that's calling that derive function. It then, in that derivation process, checks the signature and throws it out because it is an invalid transaction. And finally, when we output the L2 chain at that block, it ends up without any transactions, just ignoring it as if it is junk. So with that, we can confidently say myth busted. Great. So now that was one rollup, right? But all rollups are just slightly different derivation functions over Ethereum. That is literally for all of the rollups that exist today. They're just the same function with slight tweaks and differences. Some are more stateful than others, some are less. So a slightly different derivation function is defined for each rollup chain. So maybe we have this red derivation function for the red chain. We've got a blue derivation function. We've got a purple derivation function, all of these different derivation functions for these different chains. And they might all have different sequencers that submit blocks, and those blocks then, through the derivation process, derive the various different things that are happening on each chain. So, sending a transaction on chain A versus chain B. So if Alice wants to sync any one of these chains, basically wants to know what's happening on the chain and get the data, determine the state. If Alice wants to sync the red chain, well, first, for all of these, she needs to sync Ethereum. And then what she does is she uses that derivation function to then derive the L2 chain. And similarly, if she wants to sync the blue chain, she uses the derivation function to derive the blue chain. And, purple chain as well. This is why L2 scales, right? We talked about how Alice should not have to, as we increase the number of transactions, should not have to, increase the hardware requirements of her node. Well, she doesn't have to in this case because Alice is only syncing the information that she cares about. That is incredibly important. And that is fundamentally why this like quote unquote sharding of the execution is why L2 scales. Okay, that's multiple rollup chains. But let's talk about infinite rollup chains. Well, practically infinite rollup chains. Their infinity may or may not exist, and they're a fixed number of bytes. So it's actually just a large number, probably larger than the number of particles in the universe. So anyway, all rollup, right? We started out with all of these rollups are just slightly different derivation functions over Ethereum. Well, we can generalize the derivation function. We can say that the L2 chain is equal to derive, right? The derive function, which is standard, but we can say L1 chain, which is the same for all of these. And then we can have a extra parameter, which is OP config. That is a specific configuration for the specific chain that we're talking about. As well as we can have a standard bridge so that all of the addresses, all of the information on L1 is in exactly the same spot. So you know, given an OP config, where to look on Ethereum and how to derive the chain. This is how we get access to practically infinite chains, right? We change the config. If I change the config from having a 5 in it to a 6 in it, that's a different chain. That is, and all of these things can even counterfactually exist at the same time. So, I have the pink config, I have the green config, I've got the blue config, I've got the whole, the whole rainbow, right? It's kind of like you're looking at Ethereum L1 through a kaleidoscope. And depending on where you change the angle, if you change the angle of that kaleidoscope, you get a different chain. You look into it and you're like, whoa, oh my gosh, look at all these different chains. They're infinite chains. Okay, so anyway, yeah, that's pretty cool. That's pretty funny. But that's how you can define a simple state transition function and a single bit of node software that yields as many chains as we want. So, concept one recap, quick recap. We use that kaleidoscope over L1 with the standardized chain config to enable us to derive any number of chains. And that is how we get, boom, we have Ethereum and we use it and we get a bunch of different chains. This is not infinity. I have not depicted the correct number of chains, but it is to give you an idea. So infinite chains, that's our first thing. But notice all of these chains are fully isolated, right? You're just deriving these different chains and you can transact on them. You can change the state of them, but they can't really talk to each other or anything like that. So that is concept one. I think this is a good time for us to go through some questions if we have any.
Yeah, we got Annie has raised her hand. What do you got, Annie?
I wanted to walk through the sequencer can't forge transactions bit a bit more. Like, I'm trying to think through this of, say, Alice only submits the sequencer and the sequencer, say, we change the recipient. And in the case that Alice doesn't submit to L1, can you walk through how the derivation function makes that fail on chain if Alice doesn't have access to both sources of truth?
So when you say that fail on chain, what do you mean?
Yeah, I guess I missed the part because I assume there are still situations where these transactions fail, right? That's why the fault proof exists. So what's the limit for a forged transaction that will fail at the derivation layer?
Nice. Okay. So it is important. The fault proof is a different layer of this stack or a different abstraction. And so this is just about deriving the L2 chain, as in there is no such thing as a quote unquote failed transaction. Specifically in Bedrock, we submit our transactions to a address with no contract code at it at all. So these transactions are just recorded in Ethereum. That is all that Ethereum is doing, is that it is providing an ordering of the transactions as well as data availability guarantees. And so that means that the transaction is recorded, but if the transaction is junk, then when I sync the chain, that means this implies that Alice is not only syncing L1 to get the transaction data, and then using that to locally calculate what the L2 chain is. And in that local calculation, it includes throwing away the invalid chain. That's like the derivation function. So this is not about L1. L1 has no idea what the state of the L2 is here. Only Alice knows what the state of the L2 is.
Like if we do I think that on itself makes sense. And I think, let me just ask a more specific question. Like if we do a concrete example where, say, the sequencer changes the recipient of a send transaction, would that fail?
Yes. So what would happen is in the derivation process, there would be an EC recover that is performed on the transaction and the transaction signature. That EC recover would either recover a bogus address or some other address by chance, and basically it would yield an obvious invalid transaction. So it's literally just defined in the state transition function in the EC recover. You would be able to detect if the transaction is invalid, and you would just throw it away as your node syncs the software.
Gotcha. Wait, that makes, I totally forgot that was part of the signature. Okay, one final question. So maybe this is addressed in the other parts of the presentation, but there is, so like, are the faults that we expect to be protected against by the fault proof things like consensus faults, or is it like yeah, because I think this is the most common source of fault that people think is going to happen on an optimistic chain.
Yes. So it's actually, these types of faults are faults in the derivation process are probably not even it is part of the fault proof, right? This derivation process needs to be done deterministically by the fault proof or by whatever proof system you are using. But it is not the only type of fault, nor is it probably even the most common type of fault. Like realistically, the most common type of fault that you would see in a fault proof is someone just making a claim, I have a bajillion tokens, and they don't have any tokens at all. And they're just basically lying about something that has no backing whatsoever. That is probably what will happen. And instead of trying to get that through with, slightly modifying a transaction, they just try to get that through with like attacking L1 consensus or causing aliveness failure, censorship. Those are the types of faults that are actually like, more probable in an L1 context. But again, the block derivation or the derivation process does not have to do with the fault proof. We don't have any fault proofs yet. We are just deriving the L2 chains in isolation. So you can't withdraw, you can't communicate whatsoever to any other chain.
Thank you, Annie. Maddie, you had a question?
Hi, first time, long time. So for the kaleidoscope metaphor, how does a lens get added to that kaleidoscope?
Ooh, this is a good question. So the way that I think we haven't done this yet, but very likely what we will do is it will be the case that all of these configs have deterministic addresses, as in they are content addressable. So technically, you can start transacting on one of these chains even before any contracts with like any deposit contracts or messaging contracts are, deployed. Any like notion of that thing is around. You can literally just start transacting on that chain. And then that is actually, in some sense, they're like a lens is added to the kaleidoscope every single block, every single time there is any possible new configuration in some like abstract sense. Then in a more concrete sense, you would probably see more it happened where you deploy a bridge contract, or you deploy the config on L1 instead of just relying on the deterministic mapping of config to L1 contract. You would actually instantiate it for whatever purpose. That would make it more real and less just absolute insane infinity.
All right, we're at about 10 minutes for this concept section. So what's next?
All right, we got a solid. I feel like, okay, no, I think the first two concepts are the most meaty. Like these are definitely going to be the biggest, I think, hopefully. Okay, concept 2, cross-chain messaging. Okay, this is where fault proofs actually come in, right? And other proofs, all proofs. Okay, excuse me. So what is cross-chain messaging? Okay, it's the process by which a secure message is sent from one chain to another. Great. What does that mean? Well, let's say we've got Alice and Bob. These are just normal people. And Alice writes a message, signs it, all that kind of stuff. A letter, writes a letter. I forgot they're not called transactions. It has a to, it has a message, and it has a proof, right? The to is Bob. Obviously, the message is, hope you're doing well. And the proof is her signature. Okay. Then Mo, the mail person, goes and grabs that mail and gives it to Bob. And then Bob checks that it's, to Bob, and checks the proof, make sure that, it is Alice's signature, and checks the message. Oh, yeah, great. I'm doing great. Okay, well, what if I told you that these were chains? Oh my God, what a twist. So really what happened here, right? The real high level process here is that Mo, the mail person, is actually the person who wants this transaction to be sent. Chains don't have independent will or consciousness. They need to be kind of directed. So yes, the mail person is also kind of initiating the transaction. But importantly, Mo is saying, hey, Alice, can you migrate these tokens for me? And then Alice actually does that signing process, right? So it kind of does the state transition, I should say, does the state transition. And then that information is then communicated to Mo, the mail person. Then Mo, the mail person, goes and reroutes and relays that transaction, that information to Bob, supplying the to them, as well as a proof, which we will get into later, right? It's not quite the same. The proof is not necessarily generated by Alice chain. It is actually generated by Bob, but we're getting there. And Bob will execute the message. This is fundamentally what is happening. This is cross-chain messaging. This is the API, right? There is no other API. It's just send it to a person. What's the message? What's the proof? Okay. Now, let's talk about that from the context of L1 and L2. So if we have some tokens on L2 and we want to transfer them back to L1 because we deposited them, locked them up, and we need to send an unlock message on L2, well, what we do is we first send that transaction to L2 that says, burn the L2 version of these tokens. And then Mo, the mail person, will take that and generate a proof and send it over to L1, which then gets included. And this is a caveat, I should say. And anyway, and the tokens will be unlocked on L1. So pretty simple, right? Pretty simple at a high level. Now, notably, we don't do this for L1 to L2 because L2 is actually already knows all of the state of L1 because it's part of the derivation process. In other words, in order to sync L2, you also need to sync L1. But in order to sync L1, you do not need to sync L2. And that's why we need to have this proof, right? It's kind of as if Alice, L2 Alice, right, can read L1 Bob's thoughts, right? I don't know. That's a bit of a stretch, but we try to make things understandable. Okay. But the same process for cross-chain messaging applies from L2s to other L2s, right? I can deposit in from red chain to blue chain, and then deposit from blue chain to red chain. Again, we have the proof, which is easy, right? We have the to, which is easy, right? The you just have an address, the chain ID. The message, that's also easy, right? Very, very trivial. It's just some bytes. But the proof is really hard. The proof is what has been probably, if not, it has been the most, long and challenging thing to get right in the L2 space. But let's talk about it in very simple terms. So what is the fundamental principle of a proof? How do these proofs actually work? Well, they are explained. I will try to explain it in a way that is actually like genuinely much more intuitive. So verifying the authenticity of a message, how do we do it? Well, the way that it actually happens, if red chain is trying to send a message to blue chain, then what blue chain will do, blue chain does not have access to red chain state. It only has access to L1, right? Because it's part of the derivation process, as well as its own state, right? You obviously, a chain can read part of its own state. That's like, it's the same as a cross contract call or whatever, right? Obviously. So what do we do here? Well, blue chain will actually read the L1 chain. Blue chain has access to the red chain's config because the config is probably based on the chain ID. So it actually knows the red config. So that means because blue chain knows the red config and it knows the L1 chain and it knows the standard kind of meta derivation process, then what blue chain can do is rederive the red chain and thereby authenticate the validity of the cross-chain message. That is pretty crazy. Now, I said that, and you might notice a problem. You might be like, what is this? It's ridiculous. Because if chains are fully verifying each other, how do we get any kind of scalability? This makes no sense. What are you talking about, Karl? Right? Imagine that. If every time you wanted to send a transaction, a cross-chain transaction, you had to verify, resync the other chain, that would really just end up with a fully connected graph very quickly, right? You would almost certainly devolve into this kind of architecture or topology. So what else? What is the other bit of secret sauce that these proofs provide that a just resyncing the other chain does not actually achieve? Well, boom, it compresses the proof into something that is smaller than resyncing the entire chain. We go from resyncing every single one of these blocks of the blue chain into just doing a little bit of compute, just a little bit of compute. So there are two categories of proofs. There are fault proofs and there are validity proofs. Now, importantly, the OP stack is built to support all of these different proof types, right? We definitely should not discriminate based on the proof type. Now, by the way, I will say that we'll keep going on this point before I make that point. Now, the fault proofs, basically what you do is you prove a message is valid based on the non-existence of counter evidence. So you basically say, I think this is the case, and you wait for someone to challenge you. And the problem with this is that it requires a dispute window. There's good things about it in that it's pretty cheap to do that kind of proof. It also is definitely more flexible in that we know ways to avoid a lot of the compute scalability, proving like the proof generation constraints that we get with a lot of ZKP validity proofs. But it results in high latency, right? Because you need to wait for that challenge response period, and that's pretty annoying. The other type of proof is you have a validity proof. And so what this does is this just says, okay, I have indisputable evidence that this message is valid, at least assuming some reasonable assumptions. And this has immediate resolution because you're just proving it up front. So low latency. Those are the two kind of categories of proof. Now, I am not going to necessarily in this talk, I can talk about it more, but in this talk, I did not go into, for instance, the specifics of how a fault proof works and how exactly the dispute game works and all of that kind of stuff. But I mean, I can give an intuition here because I have gotten the feedback that it's useful. You know, in the case of a fault proof, the compute that we are compressing it into, right? It actually might even be as simple as one of these blocks, which is basically just someone on the other chain saying, hey, this is the state of the blue chain, or this is the state of the red chain. And then no response is made. But if there is a response, then you do a bisection game to find the specific opcode that you care about. In this bisection game, I guess we went 4 deep, and we ended up, you know, maybe we even executed the opcode on chain, and it was, you know, proven correct. So in other words, the fault proof systems, there's tons of resources if you want to get really deep into that. There's also tons of resources in the ZKP proof systems, which actually are pretty like they're you know, they still follow this kind of same format. All of this stuff, you know, we won't go into here, but at a high level, these are the categories. And importantly, all of these different things have different trade-offs, right? I did try to be pretty comprehensive here, because the reality is that, so we talk about on-chain fault proofs all the time, which is, you know, an on-chain interpreter that disproves, you know, some message plus a dispute game. It has high latency, it's low cost, and, you know, low trust, which is good. Low trust is good. And then we also talk about ZKP-based validity proofs, which are low latency, and that's awesome. Right now, the cost is high. Hopefully, we can reduce that very significantly over time. And the trust is also low. But the funny thing is that a lot of proofs that we use today are actually just really attestation-based proofs. These are like proofs from some set of trusted parties. And so I wanted to include that. Technically, you can do attestation-based fault proofs, which have, you know, high latency. They are fault proof, but they're low cost, but they do have high trust, unfortunately. And you can also have attestation-based validity proofs. This is like oftentimes when we talk about like cross-chain bridges with like a bunch of, you know, validators on chain A, and then you verify consensus on chain B. That's just an attestation-based validity proof, with the verifiers being the set of trusted attesters. So anyway, that's, you know, again, that's high trust but low cost and low latency. So these are the types of proofs, and you can use any one of them. And that is an important point, right? We don't need to say, okay, there has to be one proof system to rule them all, right? We can use a ZKP validity proof when we want. We can use an attestation validity proof. We can use an on-chain fault proof. We can use it all even on the same chain, right? We can have different proofs for different for different you know, use cases, which is really important, actually. So each OP chain supports all proof types. I mean, I put this in here. I mean, it's kind of like a meme, but it's like each OP chain is a compute trace, you know, is an execution trace. And so if you write your proof to support that execution trace, it will support that proof. So it's an important note, though, because oftentimes, this is the reason why I put this here, right? Because we often tightly couple the proof system to the derivation. And so I really want to be very clear that the proofs totally separate. That's just how we authenticate messages between chains. That does not determine the actual state of the chain. The state of the chain is determined via the derivation function. So let's do a concept 2 recap. First off, we started with Ethereum L1 with infinite chains. Then we added cross-chain messaging. Now they can communicate with each other, but the messages are asynchronous. That's concept 3. Okay, let's stop there. How's
All right. We got a question in the chat from Annie related to messaging. And then I want to circle back to a question from the previous section that Keith had asked. So can you share what's a light client proof in that table?
Oh yeah, a light client proof is the attestation-based validity proof. It's just like the light client. Like, okay, there is a very weird thing, which is the Bitcoin like proof of work style light client, which is not really contained here. That is like a bizarre beast. But I'm not going to. We don't need to go there. That's like, I don't even know how to categorize that. But proof of work is a little less relevant these days.
I thought a light client proof would be something like a mix of an on-chain. I don't know if it's a fault, but there's enough of an on-chain component for the trust to be low, at least according to like a really rough understanding of it.
Yeah, I mean, I think that's more just like the marketing around who the attesters are and like the vibe of the light client. Like if you have a really diverse set of attesters and there's like 150 of them and they, you know, there's a really good protocol for, you know, increase like adding a new adding a new verify or validator, whatever you want to call your attester in that circumstance, and removing one, and there's strong economic guarantees or whatever that like people are economically incentivized to not lie, then, you know, you can make a claim that that would be a very strong attestation based fault proof or validity proof, I guess. And that's fine. And I think that's legit. And there is actually a huge design space of like building out robust attestation proofs that are actually pretty secure. Like realistically, the internet runs on a multi-sig, or at least the trust of the internet runs on a multi-sig with DNS. So it is the case that like the trust is as good as your attesters. And a lot of the time with these like client based attestation proofs, they're like, they make claims about the attesters being trusted.
Nice.
Okay, circling back to chain derivation and the myth of sequencer forging transactions, Heathik just like wanted to confirm and hear you speak to the fact that the L1 will retain a record of the fake transaction, but it has no impact on the L1 and it's just used as storage.
Correct.
Can you speak to that a bit? Okay, cool.
Exactly. That is exactly it, right? The L1 is providing ordering as well as some data availability guarantees. And the L2 is only reflecting the transactions which are valid and the state transitions that are, you know, that are valid. Like just, if you're syncing L1 and there was somehow a transaction that's invalid in L1, your node would just throw it out. So a similar vibe to that.
Awesome. Does anybody else have any questions about cross-chain messaging, infinite chains, the very cute hamsters who we should protect at all costs? If not, we can, oh, Annie, you go, girl.
Not to me. So this is actually a really early question of Karl, you talking about cross-chain messaging being related to the shared bridge. It wasn't mentioned in this chapter, but like what's the connection there?
Oh, nice. Yes. Okay. So that is actually a great point. The connection there is that if you have a bunch of different bridges, then each bridge may have a different proof system and different security assumptions. And so what that does is that makes it so that you can't do the thing that I talked about in the beginning, which is abstracting away the underlying chain, abstracting away like the particular messaging solution that you have. So I should say this is actually a really good point, that even though I say that all of these proof systems are, you know, supported in some sense, it is important to note that all of these proof systems do come with their own security assumptions. And so the more people who use the same types of proofs and the same types of bridges, the more we get a like homogeneous set of trust assumptions, and that it is useful to have the homogeneous set of trust assumptions, because then we get better interoperability, right? Like if, for instance, if I deposit, if I send a DAI if I send a DAI over from one chain to the next on one bridge, and then I send a DAI over from one chain to the other using a different proof system and a different bridge, then those two DAIs are they can't be represented with the same ERC20, and therefore they are not fungible, and therefore things get more, sticky. And so it's actually very useful to have a few common proof systems and a, standardization around the bridge, so that we can ensure that as much as possible, people are coalescing around the same, types of assets and the same type of asset fungibility.
Awesome. Let's press on, I think.
Let's press on. Okay, decentralized shared sequencing. Holy cow. We're going through it all, like, oh my God. Okay. Each OP chain is assigned a sequencing protocol upon creation. So, right, part of that config, by the way, we haven't figured out what this exact configuration is, but like, I think this is a pretty safe assumption that there will be some level of sequencer configurability, some API for that to happen. For sequencers to be configured, and that is part of the OP chain configuration that we talked about earlier. So what that means is, right, we have the red chain sequencer, we might have the blue chain sequencer, but the blue chain sequencer might actually be a decentralized sequencing protocol, might be pulling from a number of sequencers in a round robin or whatever it may be. And the OP chain sequencer protocols, it could be as simple as a sequencer at a time, but maybe complex consensus. And this is nice, right? Like, ideally, we can experiment with all these different types of sequencing and still be able to benefit from the shared clients, shared, security, all of the other things that come with, the superchain. So that's great. But we're not quite done. Let's talk about this a little bit further, right? Because if you notice, our cross-chain messages, those things are asynchronous. So consider a normal Ethereum EVM smart contract. Let's say a flash loan, right? Where, contract A loans out to contract B pays it back. Well, all of this happens atomically. This gives, Ethereum smart contracts a pretty cool superpower, which is that you get basically risk-free loans if you execute them all in the same transaction. And that means that it either succeeds or it fails entirely. So that's where the risk-free part comes in. It's atomic. Now, consider contracts on two different chains. Well, each one of these chains has their own sequencers. And so contract A might loan to contract B on chain B, but that loan and payback, we don't know if that's going to happen all at once, atomically. Now, this requires, if we are going to have this happen atomically, now, notably, by the way, we can write it into our smart contract that this contract will loan and then lock itself in a state until the loan is paid back. And this contract will, lock itself in a state until that payback is, submitted. So we can actually get some form of atomicity built into the smart contract at the application layer. But this is not quite enough, because for that atomicity to actually make a lot of sense and not just cause massive amounts of stalemates where, the loan is sent out and it just causes all the chains to halt, like this chain to halt, they'll be bad. So we need to make sure that the transaction is executed on both chains simultaneously. So that means that the sequencers of these two chains need to agree that these transactions will happen at the same time in order for us to realistically get a good form of atomicity and synchronous transactions. That process by which the sequencers come up with a shared ordering, as in they say, okay, I'm going to synchronize my chain with yours for a brief period of time. That's what we call shared sequencing. So how do we enable these synchronous cross-chain transactions? Well, we can introduce economic protocols for sequencers to coordinate with each other. So instead of sequencers only sequencing one of these OP chains, they can sequence multiple, and they can have a consensus protocol for how they sequence them. And so then they come to agreement that this should happen at the same time. That transaction actually results in things happening on both of these chains. Now, these may or may not be fully protocol enforced, but there can be strong economic incentives for how to, build this. And actually, a lot of people are building this today. And by the way, the coordination between these sequencers can even happen itself on another OP chain if you wanted to figure out how that might look like. But yes, so we can build out these systems so that the chains, as they grow, as transactions are submitted to them, that they are actually submitted to multiple chains at the same time, so that we can build in atomicity primitives. So that was a very quick. See, I told you, we're actually pretty close to the end of this presentation. So we've got infinite chains. we've got chain messaging, cross-chain messaging, and now we've got synchronization between those chains. Now, notably, they're not all synchronized. Some are, running sequencers that are totally, disjoint, but a lot of these are enabling some level of synchronization, so you can provide, you can emulate the existing behaviors that you would see in normal Ethereum EVM contracts. So yeah, okay, any questions there?
John.
Nice.
Yeah, I had a question out of curiosity on just how you guys are thinking about the shared sequencer. In particular, do you envision it possibly being something similar to along the lines of like what Espresso and Astrea have talked about, where this kind of shared sequencer to scale it, like the main thing would be kind of stripping out the execution from like that actual role of ordering. And then the obvious challenge with that being you can guarantee the inclusion and execution, but like not the resulting state, like something could throw over revert or something like that. So how you're thinking about that, and obviously you would want something like a builder executing and possibly crypto economic guarantees around that.
I'm sorry, I'm gonna have to give you the most cop-out answer in the world. Basically, the answer that I will that I can really give is that the design space for synchronous, sequencer communication and shared sequencing is so enormous that I am more interested in building out a marketplace for people to experiment with all of these different designs with their various trade-offs so that we can find the thing that works the best over time with like empirical, data. Because even though I have like some random opinions that I could give, it is so complicated and there are so many trade-offs. But yeah, sorry about that horrible cop.
Okay, anybody else, or do we want to head to the final section?
But shout out to those projects, by the way. I'm super excited about all of those projects and them integrating with the OP stack. And please, that'll be very exciting. Okay, we can go on. I think we'll be chilling, and we'll be able to do it. Okay, concept 4 is the final countdown. Okay, scaling data availability. I gotcha. Y'all did not even realize that there was actually a bottleneck sitting here all the time. I talked about infinite chains. Sounds nice. It sounds great. But look at this. All the sequencers, they're submitting transactions to Ethereum L1. What's that? That's a bottleneck. Oh no, we're going to run out of data. That's why, what am I going to do? What are we going to do? So first off, right, the most obvious, and again, I tried to keep this talk to like things that are very underexplored in other talks. So I don't go into EIP 4844, but we are working on EIP 4844, an upgrade to Ethereum that increases the data availability by a significant amount. It's not significant enough to support the whole internet, but it's definitely a huge and very important start there. Now, there is a second thing that we can do. Right, that's the logo. The second thing that we can do is alternative data availability providers, such as introducing a Plasma protocol. All right, people said that Plasma is dead. Those were some haters. I told them, if you look back in those talks, everyone's like, oh, what about Plasma? We're like, yeah, we're focusing on rollups now, but we're going to get back to Plasma very soon, or not very soon, but like we'll get back to Plasma. It just has slightly worse security guarantees. And we'll go over exactly what that trade-off is. So I'm going to talk about the Plasma protocol and how we can plug in different data availability providers with a Plasma API. Okay, what does that actually mean? Plasma is really a protocol for alternative data availability providers to augment Ethereum L1 with additional data and ordering. So this little robot with a Plasma head is a Plasma data availability provider. They have an ordering of some raw transaction data. That raw transaction data that is ordered is then hashed into a single commitment, which is, 32 bytes. This is a, constant size commitment, of course, which is incredibly insane in terms of its ability to commit to large amounts of data. This is how we get to like infinite scale with true horizontal scalability. And that data, that commitment, can now be used in conjunction with the pre-image oracle, with like off-chain serving of this information. It can be used to authenticate the ordering and the availability of the data that has been committed to, which allows us, as we sync L1, to augment it with this additional data. So when we're, instead of just syncing L1 and pulling in transactions in the way that we talked about earlier, where transactions are submitted by sequencers to some, EOA or, deposits, etc., we can actually additionally pull in information that is quote unquote off-chain or shared directly from a data availability provider that augments Ethereum L1. And importantly, we can have multiple of these. Each one of them can have, can hash into a Merkle tree. Like we can get extreme scalability from this. And that is how, right, infinite chains meets infinite data, right? We're able to actually, obviously, by the way, obviously we don't have infinite data. We don't have an infinite chains. There are a limited number of compute, all that kind of stuff. Caveats. Close enough, but there's a catch, right? Well, every time, what happens if the data is not available, right? The nice thing about Ethereum L1 is Ethereum L1 guarantees data availability and it guarantees that you're going to find all of those pre-images. But these data availability providers may or may not have those strong guarantees. So in some sense, you are reliant on them being online. However, there is a recourse, because if you did this in the naive way, right, then you would, if the data availability provider went offline, they could not only make your, make the data go unavailable, they could actually start submitting a, withdrawal, a fault-proof based withdrawal. And that thing you wouldn't have the data to challenge it. And therefore you actually are vulnerable to a safety failure, not just, for instance, a liveness failure. So how do we solve that? How do we ensure that, you're always able to at least recover the data? Even if the data is gone for a little bit, you're able to recover it. Well, we can introduce a data availability challenge, right? Notably, Alice can go in and say, hey, give me the data, and sends that information to Ethereum L1. Then Ethereum L1 says, okay, well, either the data is revealed within this time frame, or I'm just going to delete that commitment. So if the data is revealed, that's fine. It's posted to L1, and now Alice can download the data. Now, notably, this fault, for all of y'all like protocol nerds, this fault is non-attributable. This is why, this data availability fault is non-attributable with respect to Ethereum L1. Ethereum L1 has no idea if Alice is lying, that the data totally was shared with Alice, but Alice just wanted to troll the data availability provider. Ethereum L1 has no idea if that's the case, or if it's the case that the data availability provider is actually, bad. And this is the speaker listener fault equivalence. Now, but what that means is Alice needs to actually pay for the data to be revealed if Alice wants the data. But so that kind of sounds bad. But Alice can locally attribute that fault. That means that Alice knows that the data availability provider was wrong. And so Alice can just withdraw from that chain and find a new data availability provider, even in the worst case. So this is a significantly better guarantee than, for instance, the data availability provider being able to steal all the money, literally. So the other alternative, right? Alice submitted that data availability challenge, but the data is not revealed. Well, then the L1 will just delete the commitment and say, ignore all of that data. Amazing, not bad. So categories of data availability, right? You have two primary categories. You have roll-up data availability, which is just all the data is on L1. It's super secure. It's super expensive. We will absolutely need to, scale that up, and we will be doing so for many years. And then we also have a nice addition, which is Plasma, the alternative data availability providers, where we are committing to data on L1 with data availability challenges. It's less secure, but it's nearly free and fully horizontally scalable. As in, the more data that people want to submit, it just requires spinning up more computers, which is not super bad. So, concept 4 recap. We had infinite chains. Now we have infinite chain. We also had infinite chain messaging. Infinite chain messaging. Not infinite chain messaging, just chain messaging. Synchronization, so that we can emulate all the atomicity things for the that we love and care about in the EVM. And we also have, quote unquote, infinite data. That allows us to actually take advantage of all of those infinite chains and all of the infinite compute that those chains imply. Because now we have an enormous amount of data which we can use to compute on those chains. And with this, we can literally build out a crazy, this architecture supports an it's horizontally scalable. So it's pretty exciting in terms of it being able to actually support the internet. And by the way, I will just say, as a fun little note, you can actually build out a single EVM abstraction on top of these primitives, which executes an emulated EVM across the entire superchain network, where each storage slot for each smart contract is its own chain. For instance, I'm not saying that this is a good idea. It requires a lot of cross-chain messaging overhead for every time two storage slots need to interact with each other. But those are the kinds of things that we're able to do once we achieve this set of abstractions. So that is the concept 4 recap, and let's do some questions.
All right. Does anybody have anything top of mind? Not a question. Oh, DC Builder. Not a question. Just want to say I really appreciate all the work that went into the cross-chain messaging layer. Using it for a project right now at WorldCoin. And it's been by far the best messaging interface I've integrated. We'll take that. That's great.
Yes.
Thank you. And then Annie wants to know, why was Plasma unable to run Uniswap at some point, which came up during a different Karl talk? Was it the security guarantee, or was Plasma a different technology back then?
Nice. No. So it was the same, and it was the security guarantee. And this is like the important caveat, right? It's not that Uniswap is fully incapable of running in a Plasma system, but it is the case that if you imagine a system where in Uniswap, the data goes unavailable, right? And you're doing a lot of transactions. The price, this is just like insane to have Uniswap go dark. Like, in other words, you need to wait the data availability challenge in the worst case, right? We're talking about data availability provider fails, right? So maybe they have very strong guarantees. They've been alive for, a long time. They've got a great reputation, blah, blah, blah. They're never going to go down, but then it goes down, right? In that case, if we are talking about that data availability provider, if there is a Uniswap chain that uses that data availability provider, then in the worst case scenario, we would see the challenge period length delay for us to get the state of Uniswap. Basically, Uniswap could just start fluctuating wildly in price, like the data availability provider would arb the Uniswap, things. Everyone would be withdrawing immediately once the data goes unavailable. But maybe it's even challenging to withdraw in this case. Things go more wrong it's just like a scarier trust assumption to rely on that. If we wanted something that is a permanent Uniswap, it doesn't really resemble Uniswap of today. Uniswap of today is this rock. It always will exist. It's just always going to be online. It's always fine. You can leave your money in Uniswap, go offline, take a vacation, etc. Here, this is more of okay, I need to actually react to this thing. Maybe I'm outsourcing the reaction. Maybe I'm whatever, but there's a lot of infrastructure that needs to be built around that doesn't fit very well for Uniswap. And this is why we made the simplifying assumption, which is just like, okay, yeah, like it doesn't, quote unquote, it doesn't work for Uniswap. I will say that, that might be a little bit of an oversimplification. It works for Uniswap in some context of Uniswap. It doesn't work for, Uniswap of, that has exactly the security guarantees that we have today.
We've got a question in the chat from Kithik. So with Plasma, deleting the commitment doesn't bring the data back if it goes out of business or whatever. Is it better for transient or time limited data, you would say?
Good. Okay, so that's a good question. The deleting the commitment, the data does not come back. It literally just the derivation process, that thing that we were talking about in the beginning, just skips over the commitment, full stop. And so it's as if the commitment never happened. The way that I would say answer the second part of that question, which is it better for transient or time limited data? What I would say to that is instead, so Ethereum, there are two kinds of data availability. There's data once available, which is like your data has been available for some period of time, and we know it has been available for some period of time. So for instance, let's say like 1 month of data availability provided by Ethereum in EIP 4844, right? So we get this guarantee that Ethereum will hold on to the data for a limited period of time, but then it may discard the data. People may delete that history. That other type of data availability is like data still available. Now, it's important to separate these two because data once available, it has a consensus protocol security guarantee, as in you need like honest majority to guarantee that data has been made available. But data once available, you just need, it's a 1 out of n, as in someone needs to be holding on to your data, at least one person. Because then you can ask, there's Internet Archive. They backed up the data. I got it from Internet Archive. I can download it. So the way that I would address the Plasma data once of it, or transient or time limited data, what I would say there is it really just becomes more important if you want to not trust the data availability provider to have a backup of your data or pay someone to back up your data, because the data availability provider is probably only providing you data once available. I mean, maybe they're providing more, but it's just much more tricky. If you want it, like you probably wouldn't want to trust that same person for that. So anyway, that's my maybe too long explanation for that specific question. Yeah, it's like Plasma is definitely similar to 4844 in its like in that respect, for sure.
Right. So we've got a couple questions, but what I'm going to ask, since we're about 10 minutes out from the official time, is that we finish the presentation and then we'll start in with Will's question and then Harper's question and just go until we feel we need to be done.
Nice.
All right.
Sick. Okay. Well, with that, the super chain, pow, knocks out the congestion, and we've, achieved the world that we all dreamed of, and, it'll take time to do. There is a, super chain MVP, I don't even know what that says. Anyway, this is just a call out, if you want a written version of a lot of this, you can look up the super chain docs. Great. So to infinity and beyond, we talked about how incredible the world will be, how incredible it'll be. Everyone will be writing smart contracts and all web applications will be designed as protocols. And we can actually use that to then fund more protocols, because the block space and the fees that are paid on that superchain go into retroactive public goods funding, which then rewards the developers who built the awesome applications that brought the value in the first place. We can actually build an open source internet and summon Ether's Phoenix using the Optimism Collective. And please join. You're a part of the Optimism Collective and you don't even know it. So this is how the superchain, is the basis for the Optimism Collective, which summons Ether's Phoenix. Welcome to the collective. Stay optimistic. Thank you very much. Okay.
Awesome. Okay, so we'll go with Will's question. Are there more use cases needing that data availability guarantee, or do you think most can get away with being a Plasma? If yes, why don't we see this already?
Great. I would say that absolutely most applications can get away with being a plasma. I think that the reason why we don't see this today is very simple, actually. It's that plasma is like strictly more challenging to build than rollups. Like, you need to build a rollup. You need to build all the rollup infrastructure, the derivation process. You need to build all the stuff that we've already built. And then you need to add on the alternative data availability provider and the challenges. And now, notably, those two things are not super difficult to do. And in fact, shout out Lattice. They'll mess around with a like hackathon version of this in a few days. But like, this is, so it's not super challenging, but it's almost like a strict superset, because think of it, in Plasma, we need to be able to derive data from L1 to get the deposits. But we also, and so in rollups, we derive data from L1 for the deposits, and all sequencer transactions are also derived from L1. So we're just pulling stuff from L1. But in Plasma, now you have to, you derive data from L1, and you derive data from an alternative data availability provider. And that's just like, it's like a little bit more code. But I do think that like there is a thing here, which is pretty funny. And that I do think that whereas we might have a lot of our, really extremely high value transactions on rollups, I think a vast majority of transactions and compute will be done on plasmas. That seems very clear to me, just given the scalability constraints of L1 and the scalability unconstraints of a plasma.
This is sort of related to Harper's question. How far are we from needing to integrate plasma as a DA for the superchain, assuming 4844 and full dank sharding work out? Why won't we have adequate DA for the foreseeable future?
Nice. Great question. It is simply because y'all are savages using the internet, clicking these buttons, pressing these things. We transmit far more than the 250 kilobytes per 13 seconds or whatever, or, even 2 megabytes, which is like the full dank sharding, 2 megabytes per second. Which is some ideas about the full dank sharding. Like, imagine if the world's data availability needs were satisfiable in 2 megabytes per second. That just doesn't make sense. So we are going to need this alternative DA and this, plasma. And that is going to get us not to 2 megabytes per second, not even to 2 gigabytes per second, not even to 2 terabytes per second. Like, we'll get crazy. Well, eventually, if the whole world is using this, I mean, we could look it up. Like, what is the total bandwidth usage of the internet right now? And it's probably a pretty large number.
Will's got a great question. Plasma has seemingly infinite names over the years. What should be the name of the next spec? It needs another name.
Hilarious. I mean, I think just generic plasma protocol. Like, we eventually figured out what plasma was after our horrible. So what happened with plasma is the same thing. By the way, this is exactly what happened with ETH2 sharding and like with a bunch of early designs. We did not have the abstraction layers figured out. And so what did we do? We come up with a new quote unquote plasma every time we wanted to come up with a new execution layer change. So we were like, okay, let's change the execution layer and then let's call this a new plasma. The part of plasma that never changed was the idea that you were committing to data and you were challenging data if it was not around. But because we didn't have the abstraction layer to realize that that's just a separate problem from the execution layer and the derivation, sorry, I should really say derivation to be consistent. The derivation, then we ended up having to scrap quote unquote plasma over and over again and like rename it because we had, because we changed something in the derivation process. So yeah, this happened in ETH2 with sharding. Like, you should see the incredible, hilarious sharding designs back in the day. Every single technology from all of these different layers were proposed in a single spec. It was like, hey, we want this from this and this. It was like tons of very specific details, and no one was able to argue with anyone else because there were no abstraction layers, so we didn't know how to cut the complexity into manageable chunks so that we come up with good solutions for each problem. Instead, we came up with this monolithic, solution for all the problems at once and ended up just totally not getting anywhere. So anyway, this is yet another reason why, abstractions are incredibly important. Thank the Lord, we're getting there.